Parametric analog signal amplification applied to nanoscale CMOS technologies. Preface. Motivation and scope. Silicon-based electronics has been one of the key factors contributing for the creation and refinement of modern and sophisticated end-user applications. Examples of these achievements are reflected by the most recent mobile platforms able to carry out very complex tasks. In fact, they aggregate in a single product complex multi-standard and multi-mode radio transceivers, e.g. GSM, 3G, Wi-Fi, Bluetooth, as well as digital processors able to reach high processing capabilities reinforced by significant amount of memory. However, these driving forces are still strongly accelerating, and therefore pushing the technology to continue to grow at a high rate. The known Moore's Law 1 for digital technology, Edholm's Law 2 for access bandwidth, and Metcalfe's Law 3 for network value try to quantify this technology escalation. At the end of 2008, more than 4 billion mobile phones were estimated to exist worldwide, representing more than 60% of penetration. Another emerging market of wireless sensor networks will tend to grow significantly in the next years, which can already reach approximately 120 million of remote units by 2010. Those huge numbers of devices results from the continuous and successful increase of the digital processing capacity and also, indirectly, from the selected supporting technology. The complementary metal oxide semiconductor, CMOS. Alternative technologies, like bipolar or gallium-3 arsenide, are less attractive for transistor density increase due to downscaling lithography issues. In the last decades, the technology has evolved from minimum device length ranging from 10 micrometers in 1971 to 45 nanometers in 2008, 4 and 32 nanometers in 2010. Interestingly, Fig. 1 shows the evolution of the installed wafer production capacity in wafers per week, WSPW, both for MOS and bipolar technologies, according to SICAS data. 5. It is clear from it that the production capacity has been completely dominated by MOS technology in last year's 1. Relative process simplicity and high manufacturing capacity contributed to lower the wafer die cost of CMOS when compared to bipolar CMOS, BICMOS, or other alternative compound of distinct semiconductor technologies. It is likely that competitive pressure will dictate that wireless applications, namely those related to a software-defined radio architecture in a single chip, which can be implemented with acceptable performance in CMOS, will be effectively implemented in CMOS. The CMOS scaling path has been evolving towards to higher integration level. In addition to this corresponding increase in device density, the process has significantly improved the switching speed, which is the result of higher transistor transition frequency feet. This is a positive improvement for the integration of analog radio frequency stages. On the other hand, the total chip power dissipation tends to be more demanding due to higher number of transistors per area unit. One of the selected countermeasure consists in reducing the applied power supply voltage, which will be as low as 0.5 volts by 2026, relatively to the transistor intrinsic gain, defined as the ratio between the device transconductance and the output conductance, GDS. This value has decreased due to higher GDS, degrading the gain achieved by operational amplifiers, op-amps, and worsen the performance of closed-loop configurations. As a partial conclusion, while Moore's law has been predictive of continuous gains in digital circuit scaling, the relative performance of analog circuits has not scaled along with digital ones. and some inherent challenges intensify with reduced supply voltage. In order to overcome some of these issues, new design methodologies both at the circuit and system levels have to be addressed together. For the design of optimum wireless transceivers in submicron and nanoscale CMOS, as digital circuitry has scaled down, it has become practical to use digital processing in conjunction with analog functions to offload some of the already known bottlenecks, making the track of digitally assisted analog an important one. At the analog circuit level, amplifier configuration stages with gain directly dependent on the GM/GDS ratio will experience a performance degradation due to lower size MOS transistors. Alternatively, new amplification approaches have to be found or recovered from earlier electronics, one of them being the parametric amplification. In a parametric amplifier (PAMP), the amplification is governed by varying, with time, the reactance value of a capacitor or an inductor. In a traditional amplifier, the gain is mostly dependent on the transconductance and output conductance, and therefore relies in the resistive type of configuration. Since the intrinsic gain process of a PAMP does depend on a time-varying reactance rather than on a resistance, it is intrinsically noiseless. Moreover, due to its simple nature, it adapts well to a low-power supply. And since this reactance can be implemented using standard digital MOS devices, it is a promising technique to be used in digital nanoscale technologies. In other words, this contributes for the task of designing a full transceiver integration in a pure digital technology towards a low-cost MOSFET-only implementation. One of the main objectives of this book is to demonstrate the use of the parametric amplification technique as an alternative approach to overcome some of the difficulties in designing traditional analog circuits. As CMOS technology scale evolves into nanoscale range, this is achieved by a set of innovative contributions, 7 to 12, that are described ahead in more detail. A modified MOS parametric cell amplifier is proposed. 9. Instead of a single MOS device, this modified cell uses two half-sized MOS devices which are connected in parallel and with one of the tied terminals left floating. As a consequence, it is shown that it becomes possible to decrease the effect of extrinsic gate parasitic capacitance during amplification phase, and therefore reducing the loading effect on the effective gain. Main expressions are derived for this class of MOS parametric amplifier cells. Application of this amplifier cell in some of the most important modern transceiver building blocks. It is shown how this cell can be used in an original passive sampling mixer, 12. In a comparator, 7, 8 for low-resolution flash ADC, and in a multiplying digital to analog D/A converter, MDAC2, for multi-step, algorithmic or pipeline ADCs, 10. Both for the comparator and MDAC residue amplifier. Analytical expressions are derived and are related with offset, gain accuracy, noise. This supports a design methodology for this type of cells. They demonstrate that it is possible to design medium-resolution 5 to 8-bit ADCs 11 using this parametric technique and without the need of post-processing digital calibration. An 8-bit 120 MHz time-interleaved pipeline ADC is designed and fabricated in 0.13 micrometers digital CMOS technology, using only MOS devices as consequence of the extensive use of parametric amplification techniques within the comparators and MDACs. It is then proved by experimental results obtained from 3 different samples that this parametric amplification technique is well suited for purely digital CMOS technology. 11.